Hi, in the previous sessions we have discussed the microbial growth kinetics, especially for the batch culture. In this session, I am going to talk about continuous culture growth kinetics. In continuous culture, what happens is that there is a continuous addition and a withdrawal of the medium. In batch culture, we say it's a closed system because we are not adding or withdrawing anything during the time of incubation. But in case of continuous culture, during the time of incubation, we are adding fresh media into the container in the culture. And simultaneously, we are withdrawing equal amount of spent media. So in every time, continuously, we are adding the fresh media. Fresh medium will have the nutrients which includes like carbon source, nitrogen source, minerals and everything. So it's a fresh sterile media we are adding into the culture, and we are withdrawing the spent media. The spent media will contain the used nutrients, byproducts, unused media components, along with the death and the living cells. Basically, they will have more of the living cells. So, in continuous culture, we are adding the media, at the same time we are withdrawing the equal amount of media, so that the rate of addition and rate of withdrawal will be always same. So the volume of the continuous culture will be constant, but the new nutrients are added to the medium, and the microbiomass is removed from the medium. So there is always a possibility of growth. Okay, the continuous culture won't leads to the stationary phase, because in order to get into the stationary phase there should be toxin limitation or a nutrient limitation. So as we are adding the nutrients simultaneously, the nutrient limitation won't be there, and toxin limitation is in a way avoided by withdrawing or removing some cells. Okay, the biomass is not accumulated in the continuous culture. During the time of withdrawing the media, we are withdrawing medium along with the microorganism. So that type of culture is called a continuous culture, and we can say in continuous culture is constant in physical and chemical conditions. Physical conditions like temperature, like pH and everything will be constant. It won't change, because as we are adding and withdrawing the media at the same time, there won't be any change in physical parameters as well as in the chemical parameters. The nutrient concentration will be constant throughout the time of culture, because it is diluted and diluted all over again. Okay, we are continuously diluting the culture, and based on this stage of growth, we can say the continuous culture microorganisms are in continuous log phase. They are growing exponentially. Okay, but the thing is that the rate of growth may not be as exponential as the batch culture. Okay, the slope, the slope of the culture may not be the as much as the batch culture. So but still, continuous culture microorganisms are following continuous log phase. There is no stationary phase or death phase, because of the continuous addition and withdrawal of the medium. We can say the continuous culture is in a steady state. A steady state means that the microorganism continue to grow in the log phase. They continue to multiply, and the chemical composition will be constant, and the number of microorganisms in the continuous culture will be the same forever, because we are withdrawing the microorganism. So we can think about it in a way that how much microorganisms are reproduced or divided in a unit amount of time. We will remove exactly same number of microorganisms from the medium. Let's say if in 1 minute, maybe in 1 hour, if there is a replication of 10 lakh cells, in the same period of time we will be withdrawing 10 lakh cells from the culture. So the number of cells will be the constant. So that's why it's called steady state or biomass equilibrium. Throughout the culture, the number of cells, the biomass, is constant in a continuous culture. And the growth rate, the growth of the microorganism, we are basically concerned about the growth kinetics. The growth rate in a continuous culture is equal to the dilution rate. Okay, how much we are diluting, that much the organism will be growing. So that's the way a continuous culture is set up. So in a way, like in a continuous culture, we are adding the fresh medium and we are withdrawing equal amount of spent medium. When we are withdrawing the spent medium, what happens, the some of the microorganism in the culture is removed. Okay, so the new medium will have nutrients. Okay, the nutrients will be utilized by the existing cells and replicate to compensate the like loss of cells during the withdrawal. So in a continuous culture, the basic point is like, in a continuous culture, growth rate is equal to the, is proportional, not proportional, is equal to the dilution rate. How much we are diluting, that much cells will be multiplying. If you are removing 1 ml of medium from the uh, culture, we will simultaneously adding 1 ml of new medium to the culture. Okay, so the rate of dilution and the rate of coming of new nutrients is directly proportional to the growth rate. So in any continuous culture, in order to maintain the continuous culture, the dilution rate and the growth rate should be same. Okay, that's the basic principle behind the continuous culture. How much media we are removing, or how much microorganism we are removing from the culture, that much reproduction will happen in the cell, because we are adding equal amount of new medium into the culture. So the basic point is like, growth rate is equal to the dilution rate. If the dilution rate is high, growth rate will be high. If the dilution rate is low, the growth rate will be low. So that's the basic principle. In a continuous culture, growth rate is equal to the dilution rate. If you are diluting more, you will get more growth. So in order to find the dilution rate in a continuous culture, we use the equation dilution rate, which is represented by D, is equal to F by V. Okay, it's a very simple equation. Dilution rate is represented by D, and F by V is actually flow rate divided by total volume of the continuous culture. The total volume of a continuous culture may be 100 ml, maybe 1 liter, or 10 liter, or 10,000 liters. So that's the whole volume. And flow rate is how much new medium is flown into the continuous culture, which will be in a way equal to the volume we are withdrawing from the continuous culture. So dilution rate can be calculated by F by V, flow rate divided by volume, and dilution rate is expressed as units in hours. In a continuous culture, if you want to know the growth kinetics, which is given by dx by dt, change in biomass in unit amount of time, is equal to rate of growth minus rate of dilution. Okay, how much microorganism is has grown, both in terms of number and size, and how much we are removing from the system. So let's say, if we are looking into the system for the to study the kinetics, we are closely observing the system for 1 hour. In 1 hour, how much reproduction, how much growth has occurred to the culture, okay, minus how much we have withdrawn from the culture, how much medium we are withdrawing from the culture. So as we are withdrawing the medium from the culture, the medium also containing microorganism. So rate of growth is the how much it is grown, rate of withdrawal, how much biomass is lost from the system due to the continuous withdrawal. So we can write dx by dt is equal to mu x minus dx. Mu x, as we know, mu is the growth rate, x is the biomass concentration, minus dx, d is the dilution rate, x is the biomass concentration. So in a continuous culture, dx by dt, the growth rate can be calculated by mu x minus dx. Mu x is the growth rate, dx is the dilution rate. So how much the microorganism has grown and how much we have withdrawn. As I said before, in a continuous culture, there is no net change in biomass. Biomass will be constant forever. Okay, the number of microorganisms in a continuous culture will be constant forever. So dx by dt, the growth in a cells in unit time will be, in a continuous culture, will be 0. It is 0 because we are removing microorganism from the continuous culture continuously, and the rate of removal of continuous culture is equal to the rate of growth. Okay, growth rate is equal to dilution rate. That's a basic principle. So the growth rate is 0. That means mu x, in order to become dx by dt, need to be 0. The mu x should be equal to the dx. That's when we will get an absolute 0. So in a continuous culture, mu x is equal to dx. We can write that, and we have x in both sides, so we can cut it down. So in a continuous culture, mu is equal to d. This is what I said before. The growth rate is equal to the dilution rate. Okay, so that's a basic kinetic principle behind the continuous culture. In any continuous culture, need to be viable, need to be stable, the growth rate should be equal to the dilution rate. Okay, yeah, we can do some more mathematical manipulations here. Here is the monod equation that we have learned earlier. In the continuous culture, we know that mu is equal to d, so we can actually replace this mu with the d. And then another thing is that the substrate concentration in this equation can be written as residual substrate concentration, because in continuous culture, especially in the chemostat, we are using a limiting nutrients to control the growth of microorganism. So we are rewriting S at SR because it is a residual substrate concentration which is used to be a limiting substrate. Okay, so D is equal to mu max into SR divided by Ks plus S, and we can actually do the we can bring this denominator to the other side. D into Ks plus SR is equal to mu max into SR. We can multiply D with the Ks and SR, then we will get this one, and we can divide the whole thing with the S, so we'll end up with something like that. And finally we can actually find the residual substrate concentration by considering the dilution rate, substrate mu max, Ks and D. So what this equation actually tell you is that how much substrate concentration is necessary to get a specific growth rate. Okay, so like if you want to calculate in the most of the continuous culture, which is need to maintain a continuous culture, we need to know how much residual substrate concentration should be provided to make it stable over a long time. So we can actually calculate the residual substrate concentration to be maintained in a continuous culture from this equation. And this continuous culture, as we know, can be maintained in two different ways. One is chemostat, which is very common, and another is Thibodostat. So chemostat, which is also called a nutrient limited self-balanced culture. In this, we are making one of the nutrient as a limiting nutrient. We are not providing it in huge quantities. We are actually controlling the growth rate by controlling the amount of limited nutrients. Okay, the growth rate, the mu, is controlled by dilution rate, of course, and in the diluted medium we'll make one of the nutrient as the limiting nutrient. Okay, and the growth is directly proportional to this amount of this limiting nutrient. One other thing I want to talk about the chemostat is the washout. So you should concentrate now. Like in a continuous culture, growth rate is equal to the dilution rate. Okay, so microorganisms should grow with the dilution rate. If you increase the dilution rate, microorganisms should be able to grow that much. In some case, we will increase the dilution rate, but due to some reasons, microorganism may not be able to grow with the dilution rate. So in that case, the dilution rate will be high and the growth rate will be low. In those times, what happens is like the microbial biomass will be reduced step by step. Continuously there is a reduction in the biomass because the dilution is high, more microorganism is withdrawn from the culture, but the reproduction rate is not that much. So what happens is called washout. Okay, after a long time what happens is like there won't be any single living microorganism in the culture. It will be totally washed out, your medium will be empty. So that's what's really called washout. So washout happens when the growth rate is less than the dilution rate. Okay, okay, when the growth rate is less than the dilution rate, washout occurs, and it leads to the decreased cell number and leads to the replacement of the growing cells from the culture. Okay, so in the chemostat basically works with the limiting nutrient. So what happens is like in a chemostat, when we are withdrawing the medium and the cells from the chemostat, the remaining cells in the chemostat will get more nutrients, so we'll able to increase the growth rate. Okay, if you are slow down if you are reducing the flow rate, the dilution rate, what happens is like microorganisms won't be able to grow. They won't get the limiting nutrients for the growth, so they will reduce the growth rate. So if there is something happens with the steady state, there will be a unbalance. Okay, the steady state will be lost. One such example is the washout, and it is a bit difficult to maintain a chemostat because there should be a fine tuning of the growth rate by the dilution rate. If the growth rate increases, it leads to the washout, and each organism has different washout points. So sometimes it is very difficult to maintain the steady state in the chemostat, especially with the new microorganisms. And there are practical difficulties because chemostat should be perfectly mixed. Otherwise, there should be maybe focal growth or wall growth that will actually destabilize the steady state. Okay, and if you are using very low dilution rate, the productivity will be low. If the dilution rate is low, the productivity will be low. If the dilution rate is high, that may lead to the washout. So it should be a perfect balance to maintain the cells. So chemostat is good. The bottom line is chemostat is good, but there should be a perfect mechanisms to control the washout. As I said, if the dilution rate is high, it may lead to the washout. If the dilution rate is low, it may lead to the low productivity. So in order to avoid that, we can do in different ways. One such thing is Thibodostat. That's what is uh, represented here. So in this, we don't have any limited nutrients. What we do, we continuously measure the turbidity of the medium, and the flow rate is actually controlled by the turbidity. Okay, there is a LED light, then a detector, just like a spectrophotometer, and this data is fed into a computer, and this computer is actually controlling the flow rate. Okay, in these cases there is no chance of washout. So washout can be avoided by using turbidostat. In turbidostat, the flow rate is controlled by actually the turbidity. Okay, there is no such thing as the limited nutrients controlled growth. Or we can use biostat. In biostat, we are controlling the flow rate by carbon dioxide concentration or pH. So it's another way of checking the microbial growth. Or else we can use the multi-stage continuous culture. In multi-stage continuous culture, that's what you are seeing in the figure. The medium is fed into one continuous culture and continuously fed into the system, and the medium is actually continuously withdrawn from it, and this effluent is used as an inoculum or the feed for the next continuous culture. So we are using two different continuous culture serially. So that's what's called the multi-stage continuous culture. It can be used for the using multiple carbon sources, or it can be used for the secondary metabolite production. As the microorganisms in a continuous culture are in a continuous log phase, we cannot directly use a continuous culture for the production of secondary metabolites, but we can use in multi-stage systems. Thank you so much for listening. Thank you.